Okay, good evening. Before get started, I have a very weak throat today. I will try to keep it short and let's focus specific about EVSE today. And before getting started, I have a quick question for everyone. How many of you have been involved in EVSE development in one way or another? Let's say EV or EVSE. How many of you involved in EVSE developments? Nobody? Everybody is new to EVSE then? That's fine, thank you. Okay then, that's fine. So what we have today is basically about some insights about what we have been doing as an embedded software development company specific towards EVSE in EV infrastructure. And let's say this is one specific use case and one specific development which I have been doing. But let's stick with EV for today in this session. Okay, so first off about myself. Myself Parthiban, and I'm an embedded software developer, and you can call me founder as well, part of this company. And I've been doing embedded software development for like past 12 plus years, starting with 2010. I started with Alcatel-Lucent telecommunication systems and worked with automotive specific for Robert Bosch. And I moved to Germany in 2016 and still with Germany like for past 6 to 8 years. And we started our own company like Linumiz back in 2020. And specific towards Linumiz, a short note is we have a brief details about Linumiz in the upcoming slides. But to be more specific, we are an embedded software servicing company based out of Berlin and as well as in Coimbatore in Tamil Nadu. So we do embedded software services. When you call embedded software services, you can think of ranging from any form of embedded hardware like processors or microcontrollers, real-time operating systems, Linux, and so on. And specific towards today's presentation, or today's talk, we will be speaking more about what is Zephyr real-time operating system and how its infrastructure is laid out and how it is basically evolving and how you can basically evolve and use Zephyr RTOS for your EV supply equipment development, that is EV charging infrastructure itself. So we would basically cover a set of standards, let's say EV standards, how to implement them, how it is available right now. That's a short overview. And then in the end of the presentation, we will see some details about our capabilities and specific towards our company and what we are expertise at. So firstly, Zephyr as a project itself is a real-time operating system project. I'm not sure how many of you have used with any form of real-time operating system or operating system. Sorry? Zephyr. Yeah, super. Like you can compare with any form of operating system for that matter. For example, FreeRTOS, TinyOS, Contiki, anything from your past. Let's say any form of let's say Texas Instruments closed source operating system and so on. So if you are involved with let's say one way or another some operating system level developments, you can think of Zephyr as a project itself as an operating system for your embedded devices. But then you cannot directly compare this with Linux systems or well-versed high-end embedded hardwares like let's say your Snapdragon SoC or Intel SoCs which runs Linux. But it is of lighter verse systems like microcontrollers, let's say ARM microcontrollers, RISC-V microcontrollers, where you get 64-bit and 32-bit microcontrollers, where you run some bare metal applications technically. So quick example would be if you get a Texas Instruments SoC, you probably develop an application using Code Compressor Studio that is closed IDE, and then you develop something on top of it. Or people used to develop things on top of Arduino and so on, right? So this is an independent operating system And the first statement, as it says, it's completely open source, and the licensing of this operating system itself is Apache 2.0, which means like you can freely modify, freely distribute. You can keep proprietary. You can play around with it without disclosing anything internally. So that is fully open source project, and the community is vibrant. When I say vibrant, it is like it is currently been heading in the direction of de facto real-time operating system for the next generation. It's been like you can think of FreeRTOS has been ruling for quite some time, as QNX said, like QNX is one proprietary and currently upcoming open source QNX softwares, and also VxWorks and other real-time operating systems. So those all has been in the market for quite some time, but with Zephyr, it's been like 8 years in the market, and now it's heading in the right direction in a way, getting into the de facto real-time operating system for all your microcontroller projects. When I say de facto, it would be in the future, which we predicted like very early in the 2018, and we started working with this from 2020 in our end. So and it is built around the secure architecture in mind and cross architecture in mind. When I say cross, as like Linux, it can run in multiple other architectures like x86, ARM, RISC-V, MIPS, and so on. Similarly, Zephyr can run in multiple other operating architectures. Like ARM is our primary goal right now, but wherein it can run in RISC-V, MIPS, like x86 QMO systems and so on. There are multiple architectures which is currently being supported, and then it can run in directly with it. So the overall development process is completely open source in GitHub, and it's vendor independent, which means like when you bound with any specific SOCs like TI, Nordic, or ST, you bound with their own software. But wherein with Zephyr, it is not the case. There is no direct bonding with which manufacturer of the SOC is controlling this. Nobody is controlling it. It's basically an independent, vendor neutral operating system maintained by the community, developed by the community. I'm not sure how many of you familiar with open source infrastructure in one way or another, but see, this is completely of an open source infrastructure that is maintained by the community. And as I said before, this is license 2.0 Apache, so you can modify, change, keep it to yourself, sell it, keep your proprietary code linked together, and produce products out of it. That's all fine. There is no problem with it. As like other licenses like BSD, GPL doesn't allow that, but Apache you can do it with, as like MIT. So, and then the certification part, right now, Zephyr is in the early stage, I would say like middle stage of development, but with middle stage, it is still capable to get the MISRA standards achieved, and also a set of secure coding guidelines achieved, means like globally recognized by various standards, and it is also officially signed by meaning you can use their stack and develop your application software or use cases, and which by means your product itself is certified on top of it. That's would be like super simple to do it instead of like developing the whole system by yourself. So let's say specific towards what exactly Zephyr RTOS can do in this case is configurable and modular. When I say the whole infrastructure itself is configurable, you can say you have a Cortex M4 microcontroller, Cortex M33 microcontroller from ST, and similarly from Texas Instruments and so on. You can still keep the application software or your use cases independent of what exactly your SOC itself is. So you can keep independent board supported system on top. Zephyr system would take care of this by means of configurable. So you can change the configurations and keep running the same software across different hardware ecosystem and hardware infrastructure. So that's 100% modular in there. And safety and secure by meaning currently like you can categorize security in like three types, usually I call it. So one is secure booting by means of boot security, and then communication security, where you talk with the external over TLS and some upper level transport layer protocols, and you store the data secure in your persistent memory. So I call this like three variants of security. In all three factors, we have Zephyr have been matured for quite some time, and there is like a security project group and committee which is underneath developing it and managing it independently. So which means like you have all three types of security brought up from the beginning of the Zephyr RTOS project development, which is like bottom of it. And specifically to speak, we can compare with any type of other operating systems if you are already familiar with. Let's say, if you people familiar with Arduino, it has been doing the embed RTOS underneath and delivering you with a set of sketches, and then you develop application and compile it into the controller. So right now, embed is obsolete. Embed RTOS is obsolete. I mean, like it is going to be end of life soon, and they adapted to using Zephyr RTOS. So it's just one simple example for doing that. But if you compare with QNX, Free RTOS, and other real-time operating system for that matter, so Zephyr is unique in many specific ways. Let's say every independent SoC manufacturer produces its own hardware abstraction layer, a software which is delivered to make the SoC functional. So those all parts of pieces which is delivered by the vendor itself. But how do you keep it functional together with the real-time operating systems like Zephyr? So it is technically like how it was done in QNX, or how it was done in FreeRTOS, how it was done in VxWorks and other set of operating systems. It's basically re-implemented from the bottom up, and then like that is totally fragmented. Let's say vendor develop its own HAL layer, but then the operating system itself keeps maintaining their own version of their own implementations for each and every IP blocks they keep it, and how to bring the SoC up and running and so on. But whereas Zephyr stands out of this crowd by meaning it consumes the HAL layer from the vendor itself. So when you get a Texas Instruments SoC, you get a HAL layer from it. You can integrate together with the Zephyr RTOS project itself, and it is already available. Similarly, you can look at how the project is organized. There are X number of HAL layers which is already integrated, and then you can readily go and use it. When there is a newer version of HAL released by vendor, we just upgrade the HAL layer. There is no changes in the Zephyr RTOS itself or the core of the kernel itself. So it just means like your software is not fragmented anymore. It just compiled together with what is delivered from the vendor. And modular infrastructure, when I say, as I said before, it is configurable across your use cases. When you develop an EV supply equipment and you choose a vendor of a hardware and you wanted to change the vendor from one SoC to another, let's say ST to TI because of various reasons, you want higher SoC capability, you wanted to change to Nordic, you want to have another capability like Wi-Fi, then you change into Espresso ESP32 and so on. So you change hardwares underneath from one variant to another from multiple vendors, but you don't change the software, because technically what you've been right now probably doing is re-implementing the whole thing or using their own new IDEs, and then you have to migrate the whole stuff into their own infrastructure. With Zephyr, you don't need to do it technically. The ecosystem just stands as is. The only thing is like you just need to change the underlying HAL layer, change a set of configurations in the SoC level, and then you just still keep the same exact applications running in a complete independent SoC without worrying about re-implementing. You just have the same application logic. You would see that in a detailed moment, sure. And as I said, this is completely open source. There is no hidden part of it. When I say completely open source, the license is kind of combined. Let's say Zephyr RTOS itself is Apache 2.0 license, but HAL vendors provide their own licensing scenarios. Let's say BSD, let's say closed BSD, proprietary BSDs, and so on and so forth. There are integrations for binary blobs, integrations for various other licenses. So that is completely open source. Means when you look into the project itself, you don't need to, let's say, worry about you need to pay for something to a vendor or an independent provider. You don't need to worry about it. So the whole source code base is completely available, and then you can play around with it on top of it. And then feature rich, which we're gonna see in this slide. So this is a simple infrastructure image copied from currently available Zephyr documentation page. So when I say feature rich, you can say the platform underneath is containing with various SOCs, sensors, ratios, and so on, and the kernel and scheduler, which is the core part of the Zephyr kernel itself. And on top, you have plenty of features. Let's say you can have a full-blown file system, for example, to play with your files. Let's say, how do you basically play with files in your Windows machine or in your Linux operating system machine? You just go and edit the file, change something, keep it persistent, and play with it, and your application probably read the configuration and work with it, something like that. So you can have a full-blown file system. It is already functional. There are like 2 file systems currently supported. For example, little fs and fat fs file system. You can work with it. So in all these verticals underneath in the OS services, you can play around with full-blown services. There are 2 key areas with Zephyr is standing out of the crowd. One is Bluetooth support. The Bluetooth controller support in Zephyr is written from bottom up, like means like which contains support for even Bluetooth 5.4 specification right now. And one other area which is full-blown support is TCP/IP stack. When you have TCP/IP stack, you can play with external connectivity, send data to your cloud, let's say over MQTT or over your backend platforms or whatever. Let's say, how do you send it? Basically, you have support for Wi-Fi, Ethernet, modems if your device is placed completely in the remote and things like that. So the whole infrastructure is somehow, you can say the OS services is super mature, and I am not going to cover each and every parts of it. You can have a look in the projects which is open source already, as I said. And as in for the security side, you have, as I said, 3 independent security: the booting security, communication security, and also the storage security. Everything is actually currently addressed and mature. And so for what we see right now is on the how Zephyr and why basically you have to choose Zephyr for your project or the next upcoming projects which you wanted to develop with when it involves like any form of microcontrollers in your setup. But with specific to EV, as I said, like I'm not sure how many of you familiar with EV and EV charging infrastructure right now. So the key challenge which we see, or at least based on the experience which we developed in our projects, what we see is the when you compare with the normal engine, which is gasoline engine or injection engine, you see you go and find a petrol pump, fill it, use it. When it is empty, you just go get another set of the gasoline or petrol or diesel and fill it, use it. That's simple, right? You're gonna find it one way or another. That's infrastructure is well set up for past, let's say 20, 30 years now, and it is mature, and you don't need to worry about it. So what comes a challenge with EV is like you have EV vehicles right now. Let's say EV from Tata vehicles or two-wheelers or any form of EV vehicles. So the main challenge at this point of time, both from the consumer's perspective and as well as the producer's perspective, is the charging infrastructure itself. Because every time Tata sells an EV car, they sell an EV charger together with it. You attach it into your home and charge it in your home. Let's say you travel around like 600 kilometers away from your hometown and return back with the same set of capacity. That is not possible because you need a charging system somewhere sitting independent in 600 kilometers circle. Right? That is not currently available. And you can compare with any form of such systems in India. Like it is not just to India, because our primary market is in development of US, Europe, and as well as in the east towards Malaysia and Indonesia as well. So we face the same set of problems because the cars like Tesla basically set up 100 kilowatts power capable EV charging systems, whereas we are still trying to achieve 25 kilowatts or even 10 kilowatts is the most predominant charging system which you can see in India. So that's the lack of infrastructure. And the primary point is, why do we lack infrastructure? The main thing is not about getting an electricity to an independent, isolated, remote location. That's not a problem. But the main problem itself is building an EV supply equipment, which is the charger itself, is complicated in many sense. Let's say building up the software, hardware, producing the standards, and then complying with the standards, and so on and so forth. So this has been a great challenge in this field, which is the main reason we see that is the for gap in terms of building the EV infrastructure compared to the fuel injection system. So that is can be probably solved with this upcoming, let's say, software capabilities and hardware capabilities and independent infrastructure development. So when you build an EV charger or EV vehicle itself, you don't need to anymore like worry about, let's say, how do we realistically build this infrastructure when we deliver to an end customer. So they have to think in a way, they have to produce an EV charging equipment which is interoperable, completely operable by anybody by any means. Let's say if there is a petrol station, you have a charging station together with it, you charge it for like 10-15 minutes and then your vehicle is charged full, then you would be happy, right? So they need to have that infrastructure. For that to have, you need to fill the gap of the capabilities in terms of building it. So that's what play a ground where we technically work on building an EVSE system. So I'm not going to speak each and every components of EVSE. EVSE by itself is a super complicated system which involves multiple other hardwares, multiple other infrastructures to be spoken with. Let's say it needs to speak with the motor, it needs to speak with the battery, it needs to speak with multiple other components independently. We call it ECUs, we call it an independent control units, manageable unit, and hardware and software and so on. We are not going to speak about all of them in here. We're going to speak only two pieces, key pieces, which is the EV car itself and the EV charger itself. So how does these two plays a key role, and what is the major part which basically can be solved with Zephyr RTOS in place? So first is the open charge point protocol. So this is the protocol which is open, which is developed in like 2009. Like it has been evolving for like now 12-13 years with various versions. Right now we are at like 2.0 version of this specification, and most predominantly adopted version of this specification is basically 1.6. And then like what this protocol states, and why do we need a protocol at all in this place? Say your EV charger sits right somewhere in your remote or in your house or some specific place which need to speak with some EV backend database, meaning you swipe in your card and then put your charger back to your car and it charges, let's say 100 watts or 50 watts it consumes and charged it, and end of the day you have to pay the money for it. Let's say as in like you got 1 liter of petrol and then you pay 101 rupee and then you come back, something like that. So you have to pay what is the amount of charge which you consume for. So for which there is always a backend system which is sitting and then developed by multiple other organizations and multiple systems. So when you develop multiple independent backend systems, how do you align with each and every charger? Let's say if I produce a EV charger and supply a backend, it works together, it's great. That was happening like from 2010 until 15, and everybody was happy. But until the point it is like you don't want to stick with the same charger and you don't want to stick with the same EV vehicle all the time. You can change your EV charger, but still you wanted to charge with your vehicle, and you wanted to change your backend system. You don't want to have any bounding with any form of companies. You wanted to be completely independent. So your backend is provided by X company, your EV charger is provided by a company Y, and then you basically got an EV vehicle from some A supplier, let's say Tesla. You don't want to have anything bound together with each other. You just wanted to be completely independent. That's the first point of solution which you wanted to achieve. How do you do this? Basically, the communication between the EV charger and then the backend system needs to be interoperable. So when I say hello, you understand what I'm saying. When I say vanakkam, you know what I'm saying. So when I say a language which you don't understand, then you don't understand what we technically speaking. So similarly, the EV charger needs to speak with the backend system underneath. Then they both need to understand the same common language to exchange. Let's say how much amount of energy this is currently consumed, how much amount of energy basically this EV charger can capable of supplying in how much amount of time. So on and so forth. There is like X number of parameters, X number of timing fields which can be configurable and manageable. So the whole thing is basically standardized, implemented by the OCPP protocol, and the goal of this talk is this protocol is now open source, meaning it has been open source standard, but there are various proprietary implementations, which is obtained by the EV charger supply equipment manufacturer. They pay the money, get the stack, and implement their applications. And they again fight with it to get it compliant with one version to another version and compliant with one backend to another backend. Then that's like a pain to figure out the whole interoperable system. So main goal is the OCPP standard is independent and open source. Open standard. So the implementation in Zephyr in OCPP is open source, which eventually been implemented by us in our company in the open source field, because our goal, our motive is open source first nature. So let's come to that. And that's one point of communication. So that's like EV charger speaking with the backend system is basically OCPP. That's how you make it interoperable. And how do you make the charge point speaking with the car, that is the EV vehicle itself, interoperable? So there are, let's say, at least a dozen of standards in between them. Like how do you make a cable, how a cable can carry this much amount of current as a capacity, and so on and so forth. Those are like X number of standards. I'm not going to speak about all of these standards in a single stretch, but we speak about only two standards. And these two standards basically involves communication between the electric vehicle and the charge equipment itself. So these two standards primarily is a proprietary standard. When you basically wanted to produce an EVSE charger, you need to get this standard and implement it. But let's say we have the knowledge about doing it and we implemented it. So the first standard, let's say IEC 61851. So how does it basically work? You have an EV car, go and park your car near to the charge station, and now it's time for you to pull up something. Let's say there is an RFID card probably given by your provider, or if technically it's an advanced technology, you have a smartphone application. You just open and log in, and then let's say access into your login. I just wanted to charge it with this. You probably going to scan a QR, and then the EV charger itself is ready. And then you pull out the cable and plug it into the EV vehicle, and then the charging starts. Once the charge ends, you pull it out and then back it into the system, and you pay the money by one way or another into the backend system. So this whole communication system, let's say from the EV to the charge point, with a human involved intermediate to initiate, close it, or let's manually do this. So that's the part of standard which has been in existence for quite some time, at least like 5 to 8 years or 10 years now in the past. So 61851 is mature and it has been currently been involved. So probably if you want an EV vehicle, probably you've been doing this if you are using a public charging infrastructure, you've been doing this already. You may be aware of it. And the next set is about the ISO 15118, which is a bleeding edge upcoming. Probably like countries in Japan, US are already done with it. Like they have a mature system for this, but we've been developing it for quite some time in India and Asia, and as well as in Europe. So how does it work? Basically, it needs to be hassle free. Means like as like our petrol station, you just put petrol, pay the money, and come back. So simple, right? So you don't need to open an application, you don't need to have an RF, you don't need to get an RF card, you don't need to have a payment gateway running in your system, and so on. You don't need to have all of this. Just simple. Take the charger and get into the charging vehicle. The charging starts, and then once the charging is done, you pull it out and then place it back. That's it. You don't need to worry about all other transaction, which means like everything is automatic. When I say automatic, that's the part of the standard which is been handling it. Meaning the car itself can speak with the EVSE over the power line, and it is basically using a TCP/IP protocol underneath, and then the standard which is living on top of it. So this whole system is plug and play, as like your USB stick, or if you plug in a USB mass storage to your computer, it is automatically mounted and you play with it. Something similar, you can say plug your charger. Once it is done, take it away and then put it back to the EV charge station. That's simple. So that is the standard which currently been bleeding, and we've been developing it and supplying it for various customers. So this is one specific use case we did develop with, let's say, a super simple microcontroller. You probably already used with it is ESP32. You might be wondering like how does an ESP32 can do an EV supply equipment? Well, that is not EVSE's complications. It is the maturity of Zephyr RTOS which helped us to do this altogether. Meaning we had to put our whole amount of time implementing the open source OCPP protocol in Zephyr, and also implement the ISO standards along with other standards into Zephyr, and that comes in the play of running an EVSE with Zephyr under ESP32. You can, comparing with ESP32, you can compare with STM32 or any form of microcontrollers for that matter. You don't need a full blown Linux operating system or a complex hardware or a complex, complex processor based systems and so on. So we did this, and then that's the main idea about this whole presentation. So now that a brief amount of information is about EVSE. Now this is like simple introduction about back to my company. We do embedded software development, as I said before. Our primary goal was initially started with embedded Linux, and then we also integrated Zephyr into our portfolio, and our security is our core goal, and we do consulting software services. We are not a hardware company, but then we are expert in electronics, and we are expert in hardware for, let's say, 15 plus years in the past. So that's our goal, and these are expertise, and in specific towards our Zephyr expertise. And we've been doing, let's say, EV and other stuff, like not just EV, Bluetooth development, USB file system, and things of this expertise. I mean, the whole team is expert with Zephyr at this point of time. So as part of our usual activity as an embedded software in open source, our open source is in our gene. So we do the whole thing in open source, and everything is in public. So you can go and find my name or my colleague's name, or the name of the company in Google, in YouTube. You can find X number of presentations done in the open source conferences in Europe, Asia, US, and so on. So these are like our public appearances in, let's say, Japan, Europe, US, and so on. Yeah, this is like simple snippet of what is our open source contributions to the open source ecosystem. Simply, like, you can go find our name. Let's say you can type Linumiz in Google, and then it would probably point you to what is our contribution to the open source. That's in a nutshell about what we did for Zephyr and then EVSE. Questions open.
For this Zephyr presentation, as it is open source, even though you are telling these news to us, then thank you very much for this thing. I used Zephyr for Nordic microcontrollers, since they are Nordic directly jumping from other RTOS and directly coming to the RTOS, so that porting is very simple, because they given all the hall layers embedded into that, and directly we can play with it. But the news you said now is we can use the same software for any microcontrollers by just changing the hall layers, right? That this I don't know about that. Say for example ESP you're talking about. So ESP is currently their idea. They will be using RTOS
free RTOS specifically.
Yeah, free RTOS predominantly. Their IDFs directly support the free RTOS, right? So you're telling that we can port Zephyr RTOS to the ESP32, but that literature and all, is it available from the Zephyr, or else you yourself, I mean your company has developed those things? That's my question.
Okay, specifically to speak about the Nordic's infrastructure, Nordic was initially developing soft devices independently on their own stack and delivering soft devices. Later they moved or migrated altogether the whole ecosystem to Zephyr. So which means like Nordic's all SoCs, is primary SDK is Zephyr now. Let's say you consume a set of implementations from Zephyr, like Bluetooth or their NB-IoT stack or Cat-M1 stack, basically from Nordic, and then you wanted to completely move to ESP32, which is capable of the same infrastructures like a hardware radio, which is Bluetooth and Wi-Fi. So as long as you can keep the upper level implementations or application under the use cases which you implemented, you keep it abstracted. It is not, if it is not specific to Nordic, your implementation is not specific to Nordic, then eventually you can change the underlying hardware as a matter of time. Let's say you change ESP32 altogether, compile it for your hardware and run the same application in ESP32, which means like there are two independent hardwares, Nordic and ESP32, and your application stands same. So if you have developed an application specific to Nordic alone, by meaning using their HAL APIs and using their vendor specific stuff, then eventually you need some time to migrate this. right, to ESP32. But otherwise, if you have used only Zephyr specific stuff for consuming Nordic, then it is just a matter of time. You just change the SoC and the hall layer and then the configuration, as I said, modular. Then eventually you should be able to do it. And to answer your second part of the question, what we help with, let's say the whole thing is open source. If you are an embedded software engineer and you have a technical team doing it already, Zephyr development on Nordic, probably they can already do this to do ESP32 as well. So there are companies, they cannot do software development on embedded scale, and let's say with our expertise in terms of security, providing over the air software update completely independent of system, which is completely remote, and migration, and keep the maintenance for the whole ecosystem for a longer time. That's what we are helping with. Let's say if you come back to us, let's say you want to migrate this to ESP32 and keep it independent of Nordic or ESP32, we can help with it. I'm happy to help with it.
Thank you for this information. Yes.
Or secure BLE as part of your offerings, like.
Yes, secure BLE by meaning the Bluetooth 5.0 specification or 5.4 specification underneath. The underlying security, it's already part of Zephyr, which means like I'm not going to invent something about Bluetooth security. It is already standardized in Bluetooth SIG and it is implemented in Zephyr. And it is a part of our offering on behalf of Zephyr. I mean, like as an open source developer, we support that. Yes.
So that essentially means that both the sites need to have Zephyr. I mean, in terms of, let's say, IoT device is there, then there is a gateway device. So both of them needs to be in Zephyr in order for it to have secure BLE.
Not ideally, and you cannot expect all of the devices in the market to use Zephyr so far, or at least now. Let's say if you get a Nest device from Google, it doesn't use Zephyr. Okay. If you get an independent home automation device, it is not using Zephyr. You cannot expect that to happen anytime soon in the next 5 years or 10 years in the market. So that's the main reason we use radio technologies to communicate interoperable. Let's say if you speak with a Linux capable home automation gateway device and your node device is basically running Zephyr in the Bluetooth side. Let's say as long as you have the same protocol underneath, let's say what protocol, GAT profile or whatever the underlying profile itself to consume data exchanges. If you understand, if you speak the both languages, you don't need to change the other side or enforce the other side to do Zephyr. In fact, the ecosystem which we technically develop involves multiple other concepts. Let's say we develop Linux, which is the gateway side of it. We develop Zephyr in edge nodes, which speak Bluetooth as well.